Okay. The time has come to show you the solution to the yo-yo problem. Perhaps you remember the problem. Here is a yo-yo, and I just let it go, and then it's being accelerated downwards. And the question is, what is the acceleration? It must be less than 9.8 meters per second square, because there is always an upward force, which is the tension in the string. We made some assumptions to solve the problem. You see here the physicist idea of what a yo-yo looks like. In my case, this is a wooden disc. This is a wooden disc, and they are connected with a smaller wooden disc, all the same material, same density. And we have assumed that the mass of the string can be absolutely neglected at all moments in time. In other words, as the string leaves this inner disc, unrolls, the mass of the yo-yo will not change. It's a negligible amount. Okay, we will also assume that as the string unwinds, that this inner radius doesn't change either, because the string is so thin. Okay. So perhaps you remember that we will assume that this disc has radius 2r, this disc also 2r, and the inner one, which is the one whereby the string is attached to, vertically up, the inner one has radius r. So if I arbitrarily call the mass of this disc here little m, then this disc has the same mass, little m, then this inner disc here has a mass 1/4 m, because the radius is twice as small. Let us calculate as a warm-up what the moment of inertia is for this disc. You should brush up on that. The moment of inertia of a rotating disc about its center and an axis perpendicular to the surface of the disc is 1/2 mr squared. But be careful now, because the r here is smaller than the r here, and the mass is 4 times smaller. So the total mass of this unit is m plus 1/4 m is 9/4 of little m. And the moment of inertia is the sum of the individual moments of inertia of these 3 discs. That comes out to be 33/8 little mr squared. And if you write it in terms of capital M, you get 33/18 mr squared. I do this now because it's conceptually very very different from solving the problem. But we will need this later. So for now, forget it, but you should be able to calculate the moment of inertia of this yo-yo as it rotates about this point. That's a must. Now, let's now first move to a object that rolls down a string, but that is not a yo-yo. That is simply a disc with radius r. So you see that here. So this is just one disc which has mass capital M, and it has radius r. And there is here a string, and we let it roll down that string, just like I did with the yo-yo. Relative to this point, there is a torque, and that torque is R cross T. This R plus T, that's the tension in the string. They're at 90-degree angles, so I can just write down RT. So the torque is RT. That is the moment of inertia, for rotation about the center of mass, times alpha. And alpha is d omega dt. So you have to refresh up on that if you don't remember this, what torques are. The only force down is gravity. At the center of this disk, we can represent this by a force down, capital mg. There are no other forces. There is only the tension up and mg down. And mg down must be larger than capital T, otherwise it would never go down, of course. So this is one key equation. F equals ma. So this force minus this force is ma. You can't argue with that, right? So mg minus t must be ma, a being the acceleration of the disk as it goes down. Now comes a key point. And this key point many of you may not have realized, but this key point also holds in the case of our yo-yo. The yo-yo is clearly always in pure roll condition. It can never slip down the wire. If I rotate this yo-yo one rotation, it must have moved over a distance 2 pi r, whereby r is then the radius of the inner disk. In this case, we only have one disk, and that's the one about which it rotates. So this is always in pure roll condition. It has to be, because it cannot slip on the string. If it makes one rotation, then it goes down the string by a distance 2 pi r. So the velocity of the center of mass on the way down, which changes with time, of course, is then 2 pi r divided by the time that it takes for one complete oscillation. Not oscillation, one complete rotation. And that changes that time. But that's irrelevant to me. Because 2 pi divided by the time for one rotation is what we call angular velocity, or called angular frequency, omega. So a necessary condition at all moments in time is that the velocity of the center of mass is omega, angular velocity of the rotating disk, times the radius. That is a condition for pure roll. The fact that this changes in time and that this changes in time is irrelevant. This holds at all moments in time. Now, if we take the derivative of this, we get that the acceleration of the center of mass equals d omega dt, which is alpha times r. Now we have 1, 2, 3 equations, and we can solve for everything. We can solve for A, we can solve for T, you can solve for everything. A equals alpha r. So I'll help you a little bit with the solution. So I take this alpha, which is RT divided by I. So A is RT divided by I times R. But I can replace this capital T by M, capital Mg minus capital Ma. Right? And then I solve for A. And this is the result. Now, in this case, we know what I is. In this case, I is very simple. It's 1/2 mr squared. 1/2 capital M, like this r squared. If we substitute this 1/2 mr squared in here, we find immediately that A is 2/3 g. Notice that m cancels. So this 2/3 g is entirely the result of geometry, not of m. You can also solve for t now. With a little bit of thinking, you can probably even guess what capital T must be. Because if the object goes down with an acceleration 2/3 g, gravity is down g. If it goes down with 2/3 g, it means that the acceleration due to the tension here must be 1/3 g up. So I predict that if you calculate capital T now, which is absolutely trivial now that you know this, that capital T will be 1/3 times mg upwards. Why did I go through this simple example first? The reason is that this equation must also be valid for our yo-yo, provided that we know that capital M is the mass of the entire yo-yo, provided that we realize that capital R is only the radius of the inner disc, right? That's the one where the string is wound around. So all we have to do, we can use this equation, we have to use capital I. That's why I calculated capital I with you already. Okay, so let us now look at, oh, I blocked the view. Let's now look at the last okay, this is definitely in the field of view. So here is that equation that holds for any object that would be rolling down a string without slip. So if you know I, then you have one equation with one unknown, which is A. Well, if you remember what I was when we calculated it for the yo-yo, maybe I can show it to you. You see it's in the right hand corner of the first piece of paper. It is 33/18 mr squared. So all I have to do now is substitute this in that equation. And I find that A is 6/17g. M cancels. It's all a matter of geometry. And that's very interesting. Think about that. The nice thing about this 6/17g is that it's not something you can easily look up on the web. It's also not something that you can guess. So almost anyone who answered me that it was 6/17g, I knew they had done it correctly. Okay, we'll leave it with this. Simple yo-yo. Of course, we calculated A not for this yo-yo, but for a physicist yo-yo, which 2 discs and a center disc. Okay, nice exercise. I will come back soon with another problem about yo-yos, but this is good enough for now. I hope you're not angry at me. I'm taping this way before I post it, so I'm very curious to see how many good solutions there will be. Have a nice day, take care, and after you see the 6/17, maybe you don't want to be friends anymore. Take care. Bye.